Hello everyone, and welcome to lecture 8 of process heat transfer. In this lecture, we will talk about design of condensers and reboilers. So we will talk about some of the basics of condensers and reboilers. We will look at what are different types of these systems. We will look at some of the design considerations, and then we will see that how these design considerations are affected if we consider different scenarios in terms of applications. And also finally we will look at the design equations of condensers and reboilers in these different scenarios. So let's look at the condensers. So condensers and reboilers are very common in process industry, and which are, for example, most of the time designed in shell and tube arrangements. It means that when we talk about design of condensers and reboilers, we are mostly talking about design of shell and tube heat exchangers. But because these systems are special, it means that they have different phase change probabilities and also different arrangement in terms of horizontal or vertical systems. So we do have to take additional considerations in design of a shell and tube heat exchanger. Another important thing that these equipments are very common when we are talking about, for example, in separation units like distillation, and most of you will be doing design in third year, and you will see that you have to have a couple of separation units, mostly distillation columns. And when you are designing a distillation column, you have to design a condenser and a reboiler, because the operation of the distillation column is dependent on the design or the duties of condensers and reboilers. Okay, so this lecture is also very important for your design project as well. In the previous lecture, we talked about design of shell and tube heat exchanger in quite detail. So the design of a shell and tube condenser and reboiler is more or less the same as design of a shell and tube heat exchanger without considering a phase change. And if you remember from the previous lecture that we calculated the overall heat transfer coefficient using this long expression, where we are actually considering the heat resistance due to convection, due to the fouling layer, due to the conduction, due to the external fouling layer, and then due to the convection at the outside the tube. Okay. And so for the case of condensers and reboilers, we are going to use same analysis. And as I said, that we have to modify this analysis considering there might be a phase change involved. Um, and also condensers and reboilers can be arranged in vertical or horizontal configurations. And if you put a heat exchanger in a vertical or a horizontal configuration, it is going to affect the heat transfer coefficients. Okay, and we will look at that how, for example, if we have a horizontal condenser or if we have a vertical condenser, how it is going to affect the heat transfer coefficient. And then we will introduce some of the primary principles in the design of shell and tube heat exchangers, okay, that we will see in the next slides. So let's now look at some of the types of these condensers. So we can have direct or indirect condensers, and if you have a cooling and the hot fluid being mixed together, these are called direct condensers, and if they are separated by a metal surface, we call them indirect condensers. And here, as you can see, that they are quite simple in design. The vapors are entering from the bottom. You spray a liquid, cooling liquid on the top, and as such, you condense the vapors. You can have different configurations from vapor spraying to packed systems, okay, where you have packing in the system, and then that helps to increase the contact between cold and hot fluid. They have a lot of advantages in the sense that they are quite cheap and simple in design. They have low vapor phase pressure drops. You can handle corrosive gas mixtures because there are not a lot of fittings and pipes and things inside the system. And also, because of the same reason, you can also avoid fouling issues in this system. They also have some drawbacks. First of the drawback is that because you are mixing two fluids, so the hot and the cold fluid, so at the end of the this condensation, you have to separate the hot fluid from the cold fluid. And then also because you are spraying a lot of water, so you do need to have a lot of cooling liquid to condense. So then we have indirect condensers, and most of the indirect condensers are in shell and tube configurations. And these can be either placed in horizontal orientation or vertical orientation, as you can see here. And the condensation can be either on the tube side or on the shell side. And heuristics normally tell us that which side we should have the hot fluid or the cold fluid. So if you have horizontal condensers, like for example here, most of the time we put the condensing fluid, like the vapors, on the shell side of the shell and tube heat exchanger, and then we have the cold fluid on the tube side. While if you have vertical condensers, like here for example, you have the condensing fluid or the vapors inside the tube while the cold fluid is in the shell. Okay, and again, why we do that, it comes from heuristics. So let's have a look at how we can develop the designing equation for a horizontal condenser. So let's assume that the condensation is happening on the shell side of the exchanger, and if that is the case, it is very likely that you are going to have a film-wise condensation on the outside of the tubes. And if that is the case, we can write the average condensing heat transfer coefficient by using Nusselt equation, and that is given here. So Hc is the heat transfer coefficient due to condensation, and we have a couple of properties from the liquid and the vapor, heat of vaporization from heat of condensation for the condensation, and then we have the temperature difference of the system. So if we ignore the density of the vapor, and in most of the cases it's like in the range of 1 or around 1, so we can ignore it, and we can simplify this equation in this form, where delta T is the temperature difference here. Okay. But this equation is developed based on the ideal assumption. So this is the ideal system where we are not considering the effect of any shear effects or non-condensing systems. But in reality, it is very likely that you have the shear stress because of the vapors on the outside of the tube. And as such, the condensation heat transfer coefficient is going to increase. And also the presence of non-condensable gases like nitrogen, for example, in your system act to decrease your overall heat of condensation coefficient. So therefore, we need to revise this equation or modify it to adopt to a more real situation. So here, if we assume a steady state system and we look at the latent heat released by condensation to the tube or a bundle of tube with tubes NT, and each of this tube is with the length L. So if you write that equation of heat of condensation released to this bundle through condensate film, we can write it as this. So where Q is the heat released due to condensation, M is the flow rate and the heat of condensation, and that should be equal to HCA delta T NT, because now we are writing for the whole tube bundle. And we can, if we know that we have a circular pipe or circular tube, we can write it in terms of the area pi d node L, because we know the length is L and the d node is the diameter of the tube. And this delta T is very difficult to calculate because it is very impractical for us to measure the surface of the tube inside the exchanger. So we can try to find a way where we can actually replace this delta T out of this equation. So we developed this equation for condensing heat transfer coefficient on the previous slide. So if we compare these two equations and try to remove this delta T, we can write the final equation in the form here. So here actually we calculate delta T from this equation and then replace the value of delta T here. So we can write this HC in the form that is given here. So this is just simple mathematics that you can do yourself. So here now, Hc, the heat transfer coefficient of condensation, is a function of the properties of the liquid film and the mass flow rate of the gas, okay, and dimensions and the number of tubes. Now, in a shell condensation where the condensation occurs outside the horizontal tube bundle, dripping of the condensate over successive rows of the tubes influence the condensing film transfer coefficient. Okay, so therefore the equation here that we developed on the previous slide needs to be corrected accordingly by considering some empirical relations that involve the number of tubes in vertical rows. However, in a tube bundle, the number of tubes in vertical rows vary according to the position of the bundle and also tube layout inside the exchanger. For example, you can have a circular tube bundle or a square tube bundle. So these are the most common type of bundles inside a shell and tube arrangement. Okay. So there are various empirical correlations available in literature to account for different tube bundle designs, and a simple empirical correlation for such prediction is given here, where HC is a function of NR, the number of tubes in a vertical row, and this NR can be calculated based on this formulation here, where Nr is the ratio of ds, that is the diameter of the shell, to Pt, that is the pitch of the vertical tube. Okay, and we can calculate this pitch of the heat exchanger based on what kind of configuration or what kind of, for example, how the tubes are arranged in this bundle. So you can have a square pitch, you can have a triangular pitch, or you can have, for example, a triangular pitch with cleaning lane. So pitch is the distance between the centers of two adjacent tubes. So based on what kind of configuration you are using in a tube bundle, you can calculate its pitch, and based on that you can calculate the number of tubes in a vertical row, and as such you can calculate what is your corrected heat transfer coefficient. So this is the expression for heat transfer coefficient when the condensation is happening on the shell side. Now let's look at what will happen if we have condensation inside the tubes. Okay, so we can still apply the Nusselt equation that we developed in the previous slides with a small correction, because if you have condensation inside the tubes, you are going to have accumulation, and because of that accumulation you are going to reduce the heat transfer. Okay, because the more accumulation you have, the more condensation you have, you are going to increase the thermal resistance due to conduction as well. Okay, and that correction factor that we use for this case is 0.8. So in this case we don't really need a correction factor for the tube layout. Okay, that like we did NR in the previous slide, we don't really need it because condensation is happening inside the tube, and as such the layout is not important because we are assuming that the condensation is the same in each tube. So this is the equation that we developed on the previous slide for heat transfer coefficient, and if you are using condensation inside the tube, then you have to multiply it with 0.8. And here you notice that we are not using the correction factor NR because we are not considering any effect of the tube bundle. Okay, so if you incorporate that 0.8 multiplied by 0.954, you can write it here 0.763. The rest of the equation is the same. Okay, so this equation is only applicable for laminar flows, because here we are assuming that the condensation is flowing inside the tubes in laminar flow. And if you want to make sure that we are in laminar region, then we have to calculate the Reynolds number inside the tubes for condensation or for condensate. So we have to use this equation 4m dot over mu ln T. And if this number is below 2000, it means we are in laminar flow, and we can use this equation to calculate the heat transfer coefficient of condensation inside the tube. Okay, so that is all for this part, and in the next part we will talk about vertical condensers and how the design equations can be developed for that system. Okay, thank you for your time.